Okay, today we are going to talk about inverse trig functions. We've used them a little bit because they give us the angle, but we're going to talk about them as functions today. We've talked about them in the past only really in 0 to 90-degree references. So inverses mean I switch y and x. So if I have y equals sine of x, to do inverse, I switch y and x. And you know from graphs from before, that means I switch or reflect over the line y equals x, or functionally, in the case of these, switch the x and y axis. So the sine of x looks like this. Oops. Those should be the same height. Let's try again. And I'm making a rough sketch because sine of x. You get to help you get the idea. Now you'll notice here that sine of y does not pass the vertical line test. And when I rewrite this solving for x, I get y equals the inverse sine. Now, this is often thought of as a kind of bad notation because it does not mean sine to the negative first power. This is not 1 over sine of x. That is cosecant of x. Another notation, and you have to know both because this inverse sine is on your calculator, but those of us in math say this is kind of a bad notation because it is often confused with this. And it doesn't mean that, even though that's what that would mean if it was written as a power. And that is where we write powers. So this arc notation is becoming more popular. It's not used on calculators, and it's not used. There's a lot of places where it's not used. So we've got this. This is not a function. However, I can make it a function by restricting the range. It does not pass the vertical line test until I do this. And again, I'm doing it in radians. In degrees, that'd be negative 90 degrees, 90 degrees. We often talk about it as restricting the domain on the sine function. Because if you remember, domain and range and inverses switch. And the key here is restricting the domain on this inverse doesn't help me because it's always between -1 and 1 for sine of y. Okay, so when I'm talking about inverse sine or arc sine, these are my domains in order for it to be a function. Okay, and we'll talk about a little bit about restricting it on inverse cosine and inverse tangent. Tangent should be pretty easy to see what we're doing. So we're going to evaluate a few of these. And actually, I'm going to go to the unit circle to do this because that's what I'm going to use to evaluate. Okay, so our first one is, it's example 1a, inverse sine of 1/2. Now, there's two places. Remember, sine is y. Inverse means what's the angle that gives me 1/2. That wouldn't be a function if I had two outputs. Remember I said that it was restricted for the domain, or actually the range, the output, from -1/2 or -π/2 to π/2, meaning I can only take from quadrant 1 and quadrant 4. Okay? So that means this is π/6. It is only π/6. It is not also 5π/6. Inverse sines or arc sines only give me values from quadrants 1 and 4. And we give these in quadrants 4 as negative angles. -π/6, -π/4, -π/3. Negative square root of 3/2. I come down here, I find it. That is -π/3. Do not give it as 5π/3. Okay. 5π/3 is not technically in the domain, so can't give our answers that way. Even though they are coterminal, yes, it is the same angle. The book doesn't actually use the arc sine notation for this one, but I'm going to. This is undefined. I am looking for π/2 as a y-coordinate. And π/2 is like 1.57, half of 3.14. So it is not between -1 and 1. Remember, my domain, what goes in here, must be between -1 and 1. So this one is not within the domain, so it's undefined. Now's when they start to get interesting. Well, the inverses undo my function. So the inverse sine undoes the sine. The sine of π/9 is something. The inverse sine of the sine of π/9 is just π/9. When it goes this way, it's very easy. When it goes this way, it's, oh, no. Oh, yeah. I guess when it goes the other way, it's very easy as well. But this one, I guess, is not quite as easy. So 5π/6 here has a y-coordinate of 1/2. I can't just say 5π/6 because the inverse sine, all answers must lie in this range. Again, that's my range, my output value. 5π/6 is more than π/2. I'm looking at a number line. Here's π/2. And then somewhere there's -π/2. Somewhere up here is 5π/6. It's not in that range. But what I can do, the sine of 5π/6 is 1/2. That's also here. The inverse sine of 1/2 is π/6. So because these all have two values, even ones that aren't here, like π/9 would be somewhere down here, they've got two values. And so I can do that. Okay. I can evaluate stuff on a calculator. Let me go ahead and get the calculator app open here. So if I want to do the inverse sine, it's just second function of sine. Looking at example 2, negative 0.81. I could close parentheses, I don't have to. And I get negative 0.944. I believe I am in radian mode. Yep, I'm in radian mode here. I can see that. I can do the inverse sine of the sine of 3.49 pi. I'm going to close parentheses since I got two. Oops. Trying to use my keyboard and not the calculator keyboard. And I get negative 1.539. And pi over 2 is 1.57. Negative pi over 2 is negative 1.57. The calculator won't give you anything that's not in the domain. So it'll just give you error if for some reason you put something in that isn't in that domain. Okay, so that is inverse sine. Inverse cosine looks pretty similar. Let's go back to the unit circle here. So we notice that our sines were the same in quadrants 1 and 2. Our cosines are the same in quadrants 1 and 4. So I don't want to use 1 and 4 again. Cosine, I want to use 1 and 2 because they're not the same in 1 and 2. That means my restricted range is going to be 0 to pi. Thus, that is the domain I'll keep on my original. So here I've got y equals cosine of x. And I can look at the original for horizontal line test because that turns into vertical line test. We'll do a different color here. Keep in mind that this is not a great sketch, but that's okay. You get the idea of the wave here. So I restrict, and I keep that part of the cosine, or this part. The domain here for the inverse cosine, again, we could write that as arc cosine. It's a funny looking S. The domain is negative 1 to 1. That was my original range. My range is now 0 to pi. Again, looking at this one, 0 to pi. My range for all cosines that don't deal with transformations, and we're not going to deal with transformations on these, is negative 1 to 1. That's inverse cosine. Calculations work functionally the same as your sines. You just use the unit circle and you have quadrants 1 and 2 for cosine. Tangent, you remember the tangent graph looks like this. Negative pi over 2 to pi over 2. With tangent from not repeating itself, you could keep quadrants 1 and 2, but it makes sense to keep this whole piece and not do split up. So we're only going to keep this middle one for the inverse tangent. So tangent of y would have all of those stacked up. Arctangent of x, or inverse tangent of x, is only going to keep that middle one. So for this one, your domain, we're going to restrict it, but this is not inclusive. Because those are asymptotes at pi over 2 and negative pi over 2. Because tangent equals sine over cosine, and cosine is 0 there, so my function is undefined. So when I switch these, my domain is negative infinity to infinity, but my range is only negative pi over 2 to pi over 2. Again, inverse tangents, I'm keeping quadrants 1 and 4, just like I did with inverse sine. And I do that so that I've got a continuous piece of function here for the graph. We can do some calculator evaluation like example 3. So the first one is inverse cosine of negative square root of 2 over 2. And actually, I would use the unit circle on this. Negative square root of 2 over 2. Right here, the inverse cosine of negative square root of 2 over 2 is 3 pi over 4. Again, I'm looking at quadrants 1 and 2. Oh, it wants me to do all of these without a calculator. Okay, the inverse tangent. Again, calculator is easy, you just type it in. Square root of 3. This is positive. So quadrant 1 is going to be positive for tangents because it's sine over cosine and both are positive. So square root of 3 over 2 divided by 1/2. This one takes a little bit of knowing things. Dividing fractions is multiplying by the reciprocal. So I knew my denominators would cancel square root of 3. So the angle there is pi over 3. The cosine of 1.1, that's an angle measure. It's going to be somewhere in here. Okay. Somewhere between pi over 4 and pi over 3. No, right around pi over 3, actually. A little bit more than pi over 3. So it's going to be somewhere here, 1.1 radians. The inverse cosine of the cosine is 1.1. That one was already in my range where I need to go. Describing end behavior. So the sine and the cosine don't go to infinity, so they have no end behavior for the inverses. However, the inverse tangent, which looked like this, pi over 2 for that y, negative pi over 2 for this y. So limit as x approaches negative infinity of the inverse tangent of x equals On the negative side, it's going to the bottom, so that's negative pi over 2. And here I'm just going to use the arctangent notation because these notations are interchangeable. For positive infinity, it's going to the upper bound, which is pi over 2. Okay. So we can compose all kinds of trigonometric functions. So compose each of the 6 basic trigonometric functions with inverse sine of x and reduce the compositions to an algebraic expression involving no trig functions. Okay, so this is going to involve the unit circle. Okay. We're going to begin with a right triangle. Okay. Now I'll go to a new page. So over here, I've functionally got a unit circle. Some of them are pretty easy. I can just read them right out of the unit circle. But we're going to do this in general. And the hypotenuse of my triangle is always 1. My angle is theta. Because we want to use the variable x, we're not going to call this one y, we're going to call this x. So I'm going to draw my triangle here. And this can apply for anything. It's got a height of x. That could be negative. That's possible. Using the Pythagorean theorem, we'll call this s. S squared plus x squared equals 1 squared. Or s squared equals 1 squared is 1. I'll subtract x squared from both sides, so I get s squared equals 1 minus s squared, x squared. And s, when I take the square root, I'd have the plus or minus, but these are lengths, so they're always plus. So instead of calling this s, I'm going to call this the square root of 1 minus x squared. This comes up as very useful in calculus. So the sine, I'm going to do all of these with the inverse sign on the inside. The sine of the inverse sine of x, remember inverse is undo, is simply x. However, the cosine of the inverse sine of x. Keep in mind, inverse sine is x over 1, opposite over hypotenuse. The inverse sine of that is theta. This triangle is functionally the inverse sine of x triangle. X over 1, opposite over hypotenuse for theta, gives me an inverse sine that is theta. The cosine of the angle theta is 1 minus square root of x squared over 1, which is simply, and I'm going to stop writing the over 1 parts. Okay, C, the tangent of the inverse sine. Again, the inverse sine of x is that triangle. The tangent is opposite over adjacent. They didn't bother to rationalize the denominator in the book. I will, just because I can, and I think it's a good practice for you. And my final answer here becomes x times the square root of 1 minus x squared over 1 minus x squared. I'm not sure that that's simpler, but it's good to see. The cosecant of the inverse sine, again, it's the reciprocal of the sine of the inverse sine. the secant of the inverse sine. Again, the reciprocal of the cosine. This one I'm not going to rationalize. I'm running out of board, and it's the same process. And it's probably not simpler. The cotangent of the inverse sine. Again, since I had to rationalize the tangent, I'll use the unsimplified version and do that reciprocal. Or the unrationalized version, so that I don't have to rationalize it later. Okay? So these are your basic calculations. We're going to talk about one application at Dodger Stadium. And, okay, this is example 6 from your book. The bottom of a 20-foot replay screen at Dodger Stadium is 45 feet above the playing field. As you move away from the wall, the angle formed, excuse me, the angle formed by the screen at your eyes changes. There's a distance from the wall at which the angle is greatest. What is that distance? So we're going to make a drawing. We've got our viewing board. It's 20 feet tall. It is 45 feet in the air. 45 degrees, 45 feet. And there's a certain distance here, x, that maximizes this angle in here, theta. Well, we know that we have these two triangles here, theta 1, and there's another one here that does the whole thing, that's theta 2. And we know theta is equal to theta 2 minus theta 1. Okay? I also know that tangent of theta 1 equals 45 over x. And tangent of theta 2 equals 65 over x. Meaning if I want this to be theta 1, I use the inverse tangent. And if I want this one simply to be theta 2, I use the inverse tangent, again, of 65 over x. And then I can take these and both substitute them into, that's a really bad arrow. And take these and substitute them into this equation. Because ultimately what I want to do is maximize theta. And to maximize, I usually use my calculator. And I probably want this in degrees, so when I get to the calculator, I will switch to degree mode. But this is my equation. Substituted both of them in there. Mode, I'm gonna put it in degree mode. I'm just gonna do divided. Oops, I have to use the calculator buttons. I'm not very good at this. Press the buttons on the calculator. Nope, I don't want alpha. Okay. My X, oh, wow, this window's, I don't need less than 0 degrees. I don't need more than 90. I know that angle's going to come somewhere between those. X scale, let's do 10. Y min. My angle is actually my Y's. Oh, my distance. My distance could be more than 90. Let's make it 200. X is my distance. My angle is my Y. My angle is probably less than 45. So I'll go negative 10 to 45. That should probably get me. Okay, I see a maximum. So I'm going to find a max. Get somewhere on the left side, somewhere on the right side. I don't care what my guess is. And my maximum angle is, or my maximum angle is about 10.47. My maximum angle is the Y's, and it's 54 feet from the back wall. So somewhere in the outfield, you're going to get the biggest angle of viewing. If you go further, it gets smaller again, as we can see looking at the graph here. So we go further. We start at the wall, everything's kind of straight up. My angle's very small, it gets bigger, and then it hits a max here. And then as I go further away, it starts getting narrower and narrower again. And we're using less of our angle of vision. Okay, that is inverse trig functions.